Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks to Dan and Jim and Microsoft for having me here. I'll be talking about Gemstone, which is one of our projects for developing the next generation cyber infrastructure environment. And let me first start off by kind of reiterating what I've been hearing for the last couple of days. In many ways, I think I'm speaking to the choir. So a lot of what I'm going to be saying is going to be very similar to what other people have said in the last couple of days. There are some slight differences in terms of the technology we're using, but let me just reiterate what I've heard. Collaboration is very important. Collaboration with the actual scientists. The PI for this project is a computational chemist, and maybe she's desperate, as Jim mentioned, but she's been really great. She's very interested in using computational resources. Has been really pushing the types of resources that she's using. So, but in general, working with scientists is a challenge, but is definitely essential for, I'm a computer scientist, so to me everything is a string or a bit or, a byte. It's all the same to me. But having that is very important. The focus on web services obviously is another theme that I've heard here, as well as the focus on thick clients, rich clients, thick clients. There was another term somewhere that was similar to that. Basically, desktop integration, right? So you want to be able to. Most people use laptops. Most people use desktops, and they want the environments to be integrated with their back-end computational environments to be integrated with their front-end computational environment, which is their desktop or laptop. And that's certainly a theme in the users that we're focusing on. So let me just start off by talking about our overall goals for this project and other projects as well. Right now, we see science as being multi-scalar, right? So crossing the different scales. By that, what I mean is that there are applications and there's science going on at the molecular level, the macromolecular, all the way up to cellular structures, organs, and whole species. So a lot of interesting science right now is occurring by spanning that scale. So, for example, there's work in taking the cellular simulations and applying that for organ simulations, right? So if you have a very detailed cell model, you want to try to apply that to how whole organs actually function. For some of the specific work that Kim Baldridge is doing, she's trying to apply quantum chemistry techniques, which are very good for small molecules, and apply them to classical molecular dynamics applications. So she's coupling different applications together to do new things, and I think that's one of the challenges. How do you build infrastructures that encourage scientific exploration? How do you build them so that you can't be an expert at different scales? So you still need to be able to use these resources, these applications at the different scales in ways that make sense scientifically. On the other end, there are the resources, right? So the resources are also multi-scale, all the way from the laptop to supercomputers to grid computing. And one of the challenges for users is that it's very complex, right? So having multiple accounts, using these different resources with different protocols, JDBC for databases, or SSH for logins and things like that is very complex. So simplifying that is definitely worthwhile. So what we're trying to do in Gemstone is we're building a framework around which applications can be integrated, right? So certainly web services are a key component. I'll talk about that a little bit. But so let's see. So easy to install, deploy, and use, right? So one of the challenges in grid computing is that it is very difficult. Supporting both the novice users as well as the more powerful users. So some kind of interface that actually allows novice users to be able to use different applications, but still doesn't take away, doesn't kind of dumb it down to the point where the advanced users are not going to use it, right? I've already talked about integrating with the desktop, laptop, but integrating services on the fly. What I mean by that is that more services are coming online. We need to be able to discover them. So having registries, having discovery mechanisms for new applications, and having the capability to integrate new applications as they come online. This work grew out of some portal work that we did. One of the challenges of web-based portal was that for new applications coming online, it was a significant amount of development work to actually integrate those capabilities. So the question that we're trying to, or one of the goals for what we're trying to address now is, well, as new applications come online, we want to automatically integrate them into the framework without any developer effort. We also, we recognize that all these applications exist. We can't sit down and rewrite all the applications. That's not feasible. We're really trying to create a framework around which the application developers themselves could wrap their applications with web service and integrate it within this framework. The existing applications with databases, for example, the Protein Data Bank, Flash applications, websites, and Java applets, there's a whole lot of functionality out there. We'd like to integrate as much of that as possible without having to replicate it. And really, let me just focus on this novel combinations of new applications, right? So we don't know exactly how the scientists are going to use the system. We're trying to provide a system where they can use it in new ways that can lead to new results. So we don't know a priori exactly what is useful. So we're trying to define a system where they can explore and find what's useful and what's not. So I'll talk a little bit about the architecture and the technology that we're using, and give a live demo maybe if I can get the resolution a little higher. And then I'll talk about the workflow integration and some future work. So our infrastructure starts off with services. It's no big surprise here, right? We use web services to essentially abstract away the complexity of the computational infrastructure, right? So when a user launches or needs to run a job, he doesn't care really where it runs, as long as he gets it fast. And as long as it's reasonable, he's usually fairly happy. At SDSC or at UCSD, we have a number of clusters. We have, roughly, well, we have a lot of different clusters in terms of what we can access for this project. There's maybe 10 or 12 different clusters on campus, which if they're not in use, we can run jobs on them, right? So 10 or 12 clusters is too many for the end user to be able to deal with, to be able to manage, to be able to query to see what's going on. And so we can essentially hide all that functionality behind a set of web services. The nice aspect of web services is a single protocol, right? There's SOAP. It's cross language. It's cross environments, and it's working fairly well. There's obviously performance issues with XML and all sorts of stuff. But the other thing that we're really pushing is strong data types, right? So if everything is a string in and a string out, there's not much, that there's not a lot of type checking we can do. There's not a lot of workflow systems that we can build across this. So we're really pushing this notion of strong data types. And one of the challenges is really to develop those data types for the different applications. So we're using XML schema to define what those data types are. They're complex XML types. We use Hibernate to map them into a relational model, so we can get them into and out of databases. And a lot of the tooling, from Access to web services to Hibernate, and all of the tooling for the code to actually make it work is already done for us, right? So it's a huge win once we can define the schemas associated with the different kinds of operations and the different kind of data. We can do schema. We can just do automatic validation of the data as well. So the business logic, right? So on the front end now, so we're starting from the back end and we're kind of moving towards the front. We do it with JavaScript, and So JavaScript provides a lot of the capabilities. It's a scripting language. It's fairly easy. It's easy to develop, easy to prototype. And we use XPCOM for kind of the deeper integration. So there's some things you can't do with JavaScript. For example, if you want to do grid FTP protocol, that's something that you have to do a little bit deeper. So you need to integrate new protocols, integrate new capabilities, maybe OpenGL or SVG or things like that. You need to do that at a deeper level. And so we're making some, creating components with the XPCOM and integrating them into the JavaScript language in that way. And then finally, you have the look and feel, right? So kind of the what the application actually looks like. And so we're leveraging CSS. It's very powerful, and you can actually do a lot with it, and it seems to be working pretty well. For a lot of the visualization, we have SVG, Flash, HTML, and other components as well. So, in dividing up the application in this way, there are a lot of benefits to doing so. One of the benefits is that you can actually hire people to do these different things, and you can find people with these particular skill sets. So I haven't talked about the application, which is written in Fortran. You can hire somebody to do that. You can hire somebody to do the web services. You don't typically want to hire the same person to do web services as doing your CSS, right? So I've done some CSS, and it looks horrible, right? I'm not the person to hire for CSS design, but you can hire very easily some very talented people to make things look very nice. And it's not just window dressing, right? I mean, people deserve professional-looking applications that work well and look nice. And we've seen a lot of the examples of that here today. And I think the users expect it and will demand it. So the focus for us. So I'm going to start and maybe give a little bit more details on our what we're doing in those 4 areas. But I'll also start with the applications themselves. So I'm a computer scientist. We're not changing the applications, right? These applications are 20 years old, maybe more, and so we can actually make modifications to the applications. They're Fortran applications. As much as I would like them to rewrite everything in a more modern way, as much as I would like them to have makefiles for building the applications, it's not going to happen, right? So we relegate that to the back end. We wrap it with web services and kind of move on. There's some particular challenges. There's no real well-defined input form. Anybody who's dealt with applications knows this, right? Every application has its own input file, has its own input file format, right? Some are space sensitive, some aren't, and it's a challenge. Some of the applications are moving towards XML inputs and XML outputs, and that's actually helping a lot. In terms of execution environments, we have a number of different software environments: Globus, Condor, SGE, PBS, Boink, and really the user expects to run under all of those. So a lot of the databases that we access have web service APIs. That's coming online. I think more than not have essentially just web pages for accessing the databases. One note in terms of the Perl and shell scripts, for a lot of the challenge in building workflows for these application domains is that in dealing with the file formats. Well, it's not just always file formats, but I'll give you an example. You can download a protein from the protein databank, the PDB database, and it doesn't have the hydrogens in it. So you need to add the hydrogens. Well, you can use Babel or you can use PDB to PQR to actually go through and add hydrogen atoms to the molecule that you have. But different programs do things in a different way, and sometimes in a right way, sometimes in the wrong way. So a lot of times, the scientist actually has to run these algorithms, have it add the hydrogens, and take a look at it and maybe even hand edit it. So it's a challenge. So for the web services layer, again, well, you can't really see that, but what it says up there is molecule calculation parameters, grid parameters, parallel parameters, and physical parameters, right? So the most important type up there is really the molecule, right? So what we're dealing with is applications that operate on molecules, and the molecules should have a well-defined type, right? What we're really pushing is having a common type for a number of different applications. And that's I think, one of the biggest challenges, is to get a community of developers together, or application developers, scientists, who do related but different work, related in the sense that they operate on the same data sets, and get them to agree on what the format should be. But we have the science-oriented interfaces using these complex data types. Some science-oriented in the sense that, when you, instead of running a job, you don't have a WSDL that says run job with the generic parameters. You actually are calculating the binding energy for a molecule, right? So if you want to calculate the electrostatic potential, then you use the WSDL that says, calculate electrostatic potential. What does that need? It needs a molecule. It needs other parameters. And behind the scenes, you do all the grid work. Scientists can understand that. They understand the data formats. They understand what it means to calculate binding energy or electrostatic potentials. And whereas they don't really understand what it means to submit a job. So we're not doing anything, really fancy with our web services. We're using Apache. We're using Tomcat. We're using Linux servers. On the back end, we submit these through Globus or SGE or other systems. We do have the GSI security. So we're using straight web services. We're not using GT4, although we're using the SSL, the security libraries of GT4, integrated with plain web services. And that seems to be working, and so we're happy with that. We have a number of different clients that are accessing a Gemstone, which is what I'm talking about today, but also other Python-based applications that are accessing these services, as well as Java-based. So that's the QMView is, I'm not sure what it stands for, but it's a visualization workflow toolkit written in Python by the Scripps Research Institute, and MBT is a molecular biology toolkit written in Java. So the front end. The front end is written in, we chose to build it off the Mozilla platform, right? So just like Firefox and Thunderbird are applications written on top of the Mozilla platform, we're building Gemstone on top of the Mozilla platform. We get all the benefits of understanding CSS, understanding Flash, understanding Java applets, but it's not just want to make it clear, it's not like a web page, it's not a web server, or it's a thick client. It actually runs on your machine. So XUL is Mozilla's XML-based user interface language that lets you build feature-rich cross-platform applications that can run connected or disconnected from the internet. So think about Thunderbird. Thunderbird is a good example. It has standard user interface components. Then you have XPCOM components that you can write to extend the capabilities. So essentially, we're using XUL to define a user interface for these web services. Web services are great because they have a programmatic API, but users don't want to use a programmatic API. They're not going to program this, so you need some way of having the user interact with it. And so we picked XUL. And one of the nice things about building off the Mozilla platform is that it really runs everywhere, right? It runs on Macs, it runs on Linux, it runs on Windows, and we've been fairly happy with the stability and the documentation and everything. So just to give you kind of an example of what it looks like, it's very simple. It's kind of like HTML, right? So it doesn't require a lot of work to build components, and in fact, it's simple enough to where the application scientist or whoever develops a web service can actually develop the user interface for that web service as well. So as an example, here are the two examples. You define a group, you can have a description, and you can define some tabs, and here you're just defining some checkboxes and some. Like I said, it's very simple. You can integrate this JavaScript. JavaScript, you can provide a lot of business logic for like what happens when you press a button and things like that.
Sorry, just a quick question. Is there, no pun intended, is there a tool for writing that XUL stuff, or do you have to write it by hand? Is it like a GUI development environment?
There are some, I think Eclipse is beginning to support XUL. Honestly, it's not that complicated, and it's sometimes easier just to do it by, I don't know, VI.
Engineers don't write XML.
What's that?
Engineers wouldn't want to write that sort of thing out.
Yeah, fair enough. It would be nice if there was some better development environments, but it's simple enough to where it's manageable. So this is kind of our screenshot. It's a little small, but you can kind of see it's a desktop application. It runs, and there are basically 4 components. I'll talk about each of the 4 components. One is this registry, right? So the registry actually just lists a set of services that are available. So we wanted to use UDDI, but it's very complicated. It has a lot of features, and we didn't really need it. So we were using RDF, which is just a version of RSS, right? So we have an RSS feed which describes which services are available. As more services become available, I think this updates every couple minutes or whatever. And so as more services are available, they show up on the user's registry. The registry, you can customize that to point to other registries, right? So, for example, we have a registry for this project which lists the services that we're running. But if you're going to use this for a class, for example, you might want to customize a registry, have a new registry that has only those services which are relevant to those classes. Or, if you have your own services running within your enterprise, you can customize that as well.
So you're not doing this really dynamically. You have kind of a keeper of the registry. I mean. When you initially said you were doing this, I was thinking immediately something like zero-conf or what I call rendezvous, where a service shows up and kind of broadcasts, "I am here." I don't know what works.
Right. So the services aren't necessarily going to be showing up on. Well, I mean, how you get into the stream, you could use, rendezvous or something like that for that. But no, that's not what I meant by that. So the services need to be registered somewhere, and so once they're registered, they actually show up here. So they're dynamic, and I'll get into what I mean by on the fly in a second. So in terms of security, we have it's a very simple. It is GSI-based security. It's much more simple than traditional. You don't need to have Globus installed on your laptop or anything like that. You type in your username, password. It talks to a MyProxy server. It actually goes through we have another project called GAMA, which provides web services functionality for doing credential management or user management. And so essentially, you're getting the proxy certificate from the server, which is a GSI certificate. And so you input your username, password, and it just uses web services to get the proxy. So on the right-hand side, you see a local file system. So this is just a view of your local file system. What you can do is you can look at the files, you can edit it, you can view it, you can browse it. One of the viewers, so if it's a molecule, for example, so again we know what a molecule looks like because we have a schema associated with it. And if it's a valid molecule, well, one might want to visualize it, right? So we can do XSLT translations to essentially translate it into SVG and then render it automatically, right? So things like that. So you'll be able to view. Now SVG works for 2-dimensional stuff. It doesn't work for 3-dimensional molecules, and especially the sizes of the molecules. When you have thousands of atoms, this isn't really sufficient. So we're looking at OpenGL-based integration. And we'll have that this year some point. In addition to the local file system, we really want to be able to browse remote file systems. So one of the XPCOM components we're writing is a GridFTP extension. So it's a Firefox protocol extension, which actually will be available outside of the Gemstone framework. So you'll be able to access GridFTP servers in the same way that you access FTP servers, right? There's no reason why you can't just type in a GSI FTP : / whatever it is, and it should just pop up a little dialog box. You should be able to enter your GSI credentials, and it should list, and you should be able to do, you should be able to retrieve files and put files in. So once we're still working on this. So they have some functionality, as you can see. But once it's available as an XPCOM component, it can be easily integrated into the local, into the Gemstone interface. So you'll have local files as well as remote files that you'll be able to browse and drag and drop across to the other parts of the interface. So then there's the main part of the interface, which is really the service panel, right? So for every service that you have, right, you have a service panel that's defined. Again, it's defined in XUL, and it's defined actually on the remote side, right? So when you build the application, the APB, in this case, it's the Adaptive Poisson-Boltzmann Solver, APBS application. So in addition to having the WSDL and the actual service itself, you actually have a XUL file there which defines the interface for that web service, right? So the people who are most appropriate to write that interface is actually whoever wrote the web service, right? They know the most about the functionality of the web service, and so they're in the best position to actually write this. So when you select on, let's say in the registry, you were to select under chemistry, there's an APBS service there. If you were to double click on that, what it would do is actually talk to the service and pull down its XUL, pull down its user interface element, right? And it would actually display that there in the service panel window. So now I have a live demo, but it's not going to work with 800 by 600. So I'll skip it, and we'll if you're interested, I can show you guys afterwards. Or 800, it's just yeah. Well, I have enough screenshots, so it'll probably be okay. So and maybe we'll get back on schedule this way too. So the service panel for APBS looks like this, right? So it has at the very top, it actually has the location of the service, where it's getting the XUL from, right?
Why is it limited to that size frame? Why?
I don't know.
Oh, okay.
I could probably fiddle with it.
No, I didn't know if the application is right. If the browser is, it's just to be off the edge.
It's no, yeah. The whole browser is okay. So this is Gemstone, but okay. So I'll just close some of these things. So again, three parts to the or 4 parts to the application. I'm just going to show you a couple parts of it. So one is log on, right? So you type in. And it actually is making a web service call to the GAMA server. The GAMA server is, you can actually look at the settings and see where the GAMA server is which GAMA server that you're using. And just to show that I'm not cheating at all, this is actually the real X509 proxy certificate that it's getting. For the registry, so this is a registry located on Athena at the NBCR.net, which is at UCSD. But you can, we have a partnership with the University of Zurich, and so if you want to see what services they're running, again, it's just an RDF file. You can see that they just have an APBS instance. So, for example, this APBS instance is running over at their site, and I can go back to the other registry. And so now there are 2 APBS instances, 2 service panels as 2 different tabs, right? And I can run jobs. So now, in terms of running jobs, there are a lot of parameters here, right? So if you want to calculate an electrostatic potential, you have this set of functionality. If you want solvation energy, you have slightly different options. In binding energy, you have, for example, you have 3 molecules you need to select. You have grid parameters, you have physics parameters. One nice thing that we just implemented is that once you set all the parameters, you can actually just you can save the parameters off in a file. and so that way you can run the same set of parameters on different data very easily. So for example, if you just drag this over here, you can see that, oops. Oh, that's the, is that the, because there are different, I think there are different versions of the panel. One is a little ahead of the other one. Let's try this. Save input, load input. Well, this is what happens when you demo. Load input. So so we do support drag and drop across molecules and things like that. I'm not sure why it's not working. But you can also just hit the button and select the file. So this, if you look at this file, it just has all this set of parameters. So for example, all the grid parameters are now set, and the physics parameters and file I/O, etc. And so if you want to launch a job, all you're really missing now is the molecule itself. And so we have a PQR file that we'll just drag and drop here, and then we'll have it run. So again, now it takes the inputs, it submits it to the web service. The web service then submits it to the clusters, and we can actually watch its execution by just with the browser window. So you can see that these files are changing. These files are being generated, and you can actually see the actual the inputs, the standard error, standard out, and everything. So those are the only things I'm going to show you on the live demo. So again, just to kind of reiterate, it's fairly easy to write these. I mean, technically, it's easy to write these. The hard part is understanding how the application, what the options for the applications really are, right? So, but because we're using XSDs, we can actually do type checking. So if you try to drag and drop a molecule somewhere where it shouldn't be, then it should actually not let you do that, or it should complain about it. I'll get to, oops. So in terms of the framework itself, right, so the XUL is being loaded into the Gemstone framework on the user's machine. So what does the Gemstone framework actually provide? It provides service discovery, it provides drag and drop capability, it provides the access to the local and remote file systems, inter-application communication. So for example, if you have multiple different applications, and as you interact with one, it should affect the other. Doesn't currently provide that, but it's in newer versions of this, as we develop it, that'll be some of the functionality that the framework has. It provides access to the X509 credential, and it provides a little bit of security as well. You're not just downloading some random JavaScript that you're running. You're downloading random JavaScript which is running within Gemstone. So now it's our problem to try to make sure that it doesn't do anything bad. So the other thing is that since all the actual work is being done by the web services, right? So all the business logic is done in the interface, but as it, the real work is still done by the web services, and we're capturing all that, right? So we're capturing as the user is hitting, the run button. So we know exactly when they make the call and run applications they're running. We also know which files they're dragging and dropping across, right? So in terms of a workflow system, right, what we're really kind of envisioning is that similar to Excel's macro recorder, right? So as the user is interacting with these different services, dragging and dropping files that are produced from one to the other, the system is creating a workflow description of what the user is doing, and that can be replayed and can be saved and actually published. So this gets to the workflow. We have a very simple workflow description that's based on a previous project that we had at Informnet. There's I think a lot of similarity between what we were doing, what Dennis Gannon talked about yesterday, and what the Sangam is doing that we heard about today. So it's a simple DAG. It's an XML description of what the workflow looks like with the web services nodes. One of the challenges, of course, is how do you do the data management between the different nodes? And we heard about it. The Sangam was doing one way. I think Dennis I talked to him that he's doing it slightly differently. So we're in the process of kind of building this out. We have something where it's working for some simple workflows, and using the XML complex types, it's a little more challenging. One of the key things that we think in terms of the workflows is once you publish a workflow, that workflow should itself be accessible as a web service, right? So there's whether you're accessing 10 different services, right? You should access the workflow as a web service. Then you get all the discovery, and you get all the security, and you get all the other capabilities of web services in that way. So we've been operating for about a year with this in this project, and we have essentially, if you go to that URL, you can download it. It's a Firefox extension, so you can go there, and it's an XPI file. It installs very easily on Firefox. Currently, the applications that we're supporting right now is we've been doing a lot of work on APBS, getting that finished up. But now that we have that done, so APBS is the Applied Boltzmann Applied Poisson Solver. LigPrep is actually a rotational confirmation tool. PDB is the protein database. Babel does file conversions, and QMView does some basic visualizations. So that's stuff that we have working right now. GAMES, which is a quantum molecular dynamics application, should be ready fairly soon, along with some other quantum mechanical Siesta, which is a chemistry physics application. So we're really looking we're developing the first initial set of applications, but we're working with other application developers so that they'll be wrapping their applications and providing the interfaces. So there are a lot of people who are involved in one way or the other. First, NSF has funded this work. NBCR is providing the web services infrastructure on the back end, and University of Zurich, Kim Baldridge has a joint appointment with them, so her graduate students are spending a lot of time with us, helping us understand exactly what their needs are. So I'll leave it there. There is. Yes. Well, we have 3. Okay.
Cool. Good job.
Thanks.